Welcome to Biota.org Interviews. I'm Tom Barbalet, and today I have the pleasure of talking with Professor Paul Johnson, a professor of political science at the University of Kansas. Professor Johnson, for people not familiar with you, can you please give some discussion to your background and how you got interested in artificial life?
I did my graduate work at Washington University in St. Louis, where we were focused on game theory and rational choice models of how people behave. But those models are very mathematically intractable when you introduce heterogeneity or a variety of different types of actors or different behavioral premises. And so when I was struggling with some difficult mathematical models, John Castee, who was a professor at the Santa Fe Institute, and he wrote several beautiful books about artificial life, he visited our university and gave a research presentation that talked about complex systems models, the so-called L-Farol problem, and programming exercises that were being done in Santa Fe and Albuquerque about traffic and maybe soccer players or football players, I can't remember. But that was when I seized on the idea that we could use computer representations to make more elaborate models of individual people and how they behave and study the aggregative patterns that are observed.
Now, you are the current maintainer, or one of the maintainers, of the Swarm project. For people not familiar with Swarm, can you please give a kind of Swarm 101 background?
Yes, sure. There's a really wonderful book called Complexity by Waldrop, and in that book, it has the personal life stories of Chris Langton and Brian Arthur and Stuart Kaufman. And in that book, he describes the development of this idea that our view of systems should be built up from a lot of small, simple components that interact in a way so as to develop on an individual basis and then to react to their environment and change their environment. So if you really wonder what the idea is and you want to see the very interesting story of some of these great scientists, that book, Complexity, really will help people a lot. So if you think about this idea of having these small, separate components that act according to various principles, you eventually arrive at the idea that we could use a computer to design these models. So in the early 90s, I had done my own simulations in Pascal, but I ran into the problem that there are just too many separate components in a simulation model for an individual author to make a model that is useful and also understandable to other people without some kind of a common framework. So Swarm originally was supposed to be a common set of concepts and model building techniques that would allow us to exchange our findings in a way that is scientifically replicable. So with this idea, the team at the Santa Fe Institute that included the leader was Chris Langton, and there was an employee from John Deere, Roger Burkhart, and some staff members, Nelson Minar Askenazi, and then later Glenn Rapella, and then Marcus Daniels. These people started fleshing out this system to describe the creation and development of individual units that do things, and then as scholars we can adjust the things that they do and study the effects that they cause. So if you're not a programmer, I suppose that this is all gibberish to you anyway. You can just imagine some common game like SimCity 2000 where the little people run about from home to store and back again. You can imagine that a swarm model is like that, except that the guts of it are laid open researcher to consider various behaviors that the agents might carry out and study their impact on the system. So then Swarm was in an incubator from like 1994 until the release of version 1.0 in 1997. That was the summer that I started learning more seriously about programming and Swarm, and I had a small grant from the National Science Foundation in the U.S. to work on that. Very quickly, I realized that one of the problems in the Swarm community is that most of the people were good programmers, but not very interested in teaching the people who don't program like me. And so when I would learn new things, I would jot them down, expecting that I would teach a class someday, which turned out to be true. So eventually those things that I wrote down became the frequently asked questions list for Swarm. And then as my programming skills grew, I started contributing small bits to the Swarm language itself, library itself, but also I started making up the packages of Swarm for people who use a Linux operating system. And then in 2000 or so, we put together the user guide for Swarm. So after that, my role was mainly to try to implement new features in the Swarm libraries that I wanted to see. And for Swarm, the newest version of Swarm, I put together the new version of example programs that people can use to explore the ideas behind Swarm.
Now, the software itself, Swarm, how has Swarm evolved from Chris Langton and the original group's original thesis into contemporary Swarm?
Well, let's see. Well, I think that the idea, I'm not sure what their original idea was, and I'm not sure that they all agreed about what it should be, to be honest. The way Swarm originally was, it was a programming library written for people who use the language Objective-C. And Objective-C was, it's the language that the Apple operating system was written in, and it was the language that before it the NextStep operating system used. And I really like it because it's the C language with a very simple set of extensions to allow you to think of things off in the computer's memory as self-encapsulated objects. So Swarm started out as an Objective-C framework which had the following main purposes. Number one, it had a set of random number generators that were, well, not prone to the mistakes that were common at that time in simulations, and statistical distributions that use those random numbers. It had a scheduling framework so that you could design a model that was either of two types. You could design an ordinary type of simulation model in which all of the agents are thought of as pieces on a checkerboard, and they all do something at the same time or one after the other. So that standard kind of scheduling system existed. In addition, there's one of the big innovations in Swarm is this idea of a dynamic event-driven schedule where something happens at one spot and it triggers an event that happens, say, 2 or 3 time steps in the future at some other spot. And so you can have a leapfrogging of events through time. And then Swarm has this graphical interface through which you can interact with simulations if you choose to. So that was the original system. It was written for Unix computers, and if you didn't know about Unix, you couldn't use Swarm, frankly. And so that was when I was a Windows user. I was an avid believer in Windows 95. I was in the beta program for that. So it was a little bit of a stressful experience for me to change from using Windows to using Linux. But after I understood the difference, I never regretted changing over because Windows just seems horrible in retrospect. But anyway, at the beginning, Swarm was this set of tools that you could use to write programs in the language Objective-C. Java language was introduced. And there was a lot of curiosity from people who used Microsoft Windows, and a lot of curiosity from people who were learning this new language Java to see if it could work with Swarm. So in 1998 or so, Marcus Daniels was the lead programmer on the effort to make Swarm run on the Windows framework that's known as SIGWin. SIGWin is a free toolkit that can be installed in Windows systems. Inside this SIGWin environment, you can compile Unix programs and run them as if you had a Unix computer. So Swarm became usable to people who have Windows. And then 2 years after that, Marcus Daniels used the so-called Java native interface to allow people who write programs in Java to access the features of Swarm. And there were examples of several classic Swarm programs that had been written originally in Objective-C that were translated and written in Java, so that if somebody was an avid Java programmer, they could study those examples and then see what to do in order to make their own models. The Java support in Swarm was mature in about 2001 or so, maybe 2000. After that, Marcus Daniels started working on a scheme to allow people who write in C++ or other generalized other languages to interact with Swarm through this. It's kind of like a Corba environment. It's like Microsoft.NET potentially could talk to Swarm, and so I don't think that work has ever been completely finished. But if you happen to be an avid C++ programmer, and there are some in Australia that do this, you can make a program in C++, talk to the Swarm libraries to get your job done.
Now, in terms of the breadth of users and uses for Swarm, can you give some discussion to that and give some examples of third-party users of Swarm?
Sure. My colleagues in political science think that it's quite funny that I co-authored a paper on ballet dancing. In this ballet model, we have little agent dancers who decide which steps to take up and where to go on the basis of where they've been on the dance floor and what the other dancers are doing about them. And then my co-author turned this into a little animated movie of stick figures doing pirouettes. So you can use Swarm to represent individual agents doing basically anything you're interested in. So the simulation of the stock market was one of the famous simulations done at the Santa Fe Institute. And there's a Swarm version called the ASM, the Artificial Stock Market. I had an article about that in Social Science Computer Review. There are people, I get emails from people who want help with projects that are medical related. People are simulating the movement or interaction inside your body of your organs. So sometimes the simulations that people are doing are very fine grained, thinking about enzymes in the liver, which I can't tell you anything about why it was meaningful, but there's a ecologist named Steve Railsback, who I met when I first started working on Swarm. He was a beginner, just like I was. And he has just had phenomenal success using Swarm models to represent the movement of fishes inside rivers and dams. And he gets research projects funded to study the movement of fish in the Pacific Northwest. There was a large National Science Foundation funded project in the biocomplexity initiative about 4 years ago. This started at University of Michigan, the Complex Systems Center there, and several people from several other units had a very large grant, several hundreds of thousands or perhaps even millions of dollars. And they were developing a very detailed simulation model of the growth of the urban areas and their impact on the environment in Michigan. I know that the people who do economics and financial markets have put out either 2 or 3 different volumes of swarm models written studying exchange and trade. Maybe one of the most famous simulation models for social scientists is the one by Epstein and Axtell. It's in a book from Brookings called Growing Artificial Societies, and that's a model of a stylized society in which agents try to accumulate sugar, which represents wealth, and they dissipate sugar as they go about their affairs and possibly either die or they prosper. And there's a swarm version of the sugarscape, or sugar space. One of the favorite simulation models for me is about forests. Melissa Savage, professor at UCLA, was in a team that developed this arbor games model in which there are as many different kinds of trees as you would like to consider, and they all have different features about how many seeds that they emit under what conditions, and whether they grow if they're exposed to too much weather or sun or too many close crowding trees. And once you can insert forest fires to study the impact of forest fires on the growth of particular species in a forest, and you can study the sustainability of diverse trees.
You touched on the use of swarm as an A-Life model in the social sciences.
Right.
Have you seen any other A-Life programs used in the social sciences, and what more would you like to see from A-Life developers in terms of things that can be useful in the social sciences?
Well, I may be in the minority on this. I'm not a big fan of Java. So, for example, at the University of Chicago, an alternative swarm-like program developed called REPAST, REPAST, and it was originally presented as the Java version of Swarm. It has basically the same ideas, although, it's like anything else that you let programmers be in charge of. It changes and grows in a way that's rather like artificial life. REPAST now is quite elaborate as a framework, and it involves several different programming languages, and they're recommending that if you're going to write your simulation now, you use Python with objects. So REPAST is pretty well known and well regarded. I don't have such good experience with Java as a language, so I can't get really excited about that. I would say that after REPAST and Swarm, the most frequently used framework for simulation is none at all. Many of the people doing these models just think they'll write it down with C++ and be done with it. Now, of course, they're passing up the opportunity to work within a common framework, so their work can't be inspected in the same way that it could if you used one of the toolkits. But I'm afraid of giving people a toolkit with too many advanced features, because if you give it to people who don't understand what they're doing, they will just take it and try and use it for every problem, whether it's suitable or not. I'm reminded of the introduction of SPSS. It was a computer package in the 60s, a statistical package for the social sciences. It still exists today. It's very well marketed. When SPSS came out, social science was changed in a way that wasn't altogether good. It was as if we set loose a whole bunch of junior high students with hammers looking for nails, and so our journals became filled up with examples of things SPSS could do as versions of social science. And I'm not entirely confident that was a good idea. So I'm skeptical about these people who talk about creating a simulation paradigm that non-programmers can use, because I think that what that will end up doing is taking whatever examples programmers create, and social scientists will begin to reinterpret the things they do in light of those program examples. If you've ever run Swarm, or you look at the website, you'll know that it comes with certain example programs. There's one called Heatbugs that Chris Langton wrote. And in Heatbugs, what happens is there are these little agents called bugs who emit heat. And then some of the bugs think that their current position is too hot for them, so they run away from their own heat. And other agents are too cold, so they go to find the heat that the other agents create. And you can interact with these models and make the bugs hotter or colder, or want it to be hotter or colder, and you can watch them as they search about for just the right temperature. So once you see these swarm examples like heat bugs, then if you really don't understand what you're doing, you end up going out to the world and looking at something, and then you end up straining the metaphor of the heat bugs to apply to whatever problem you study. So I think that for social science, or maybe for any kind of science, well, we don't necessarily need highly refined tools to work on specific kinds of things. I think what we need is help at learning how to program and how to use general purpose libraries, and help in explaining ourselves to each other, if you can see the difference.
Maybe feeding into that, but maybe as an abstract question as well, what more would you like to see with the artificial life community?
Well, how long has this been going on now? 15 years, maybe? I think that it's about time where we should start to have a coalescing of understanding about what is different about this kind of research and what's not different. So, have you seen that book that Stephen Wolfram wrote? I guess 2 years ago now. It's called a different kind of science, a new kind of science. It's a very large book. In fact, it's such a large book that one of the students in my department replaced a monitor stand with that book. It's just a voluminous statement of everything Wolfram believes he's found out by studying cellular automata, and very simple ones at that. That's certainly part of artificial life, what most people think of as artificial life. What I wish we could get from artificial life is instead of quirky examples of funny things, like when I think of artificial life, I think of Chris Langton's virtual ants, and I think of Tom Ray's computer simulation model, where the programs try to develop their own code to take over as much CPU as possible. And I think of Stuart Kaufman's studies on the origins of life. So those are some basic ones that I think of in that framework. And what I really wish we could get is a coherent understanding of what are the benefits from looking at things in this way. What are we finding out that's different? The problem is that when the people who understand those models consider trying to work out the connections that we need to understand, either they think it's too obvious to write it down, or they try to write it down in a way that translates it into the jargon of the older scientific paradigms. Sometimes they'll try to translate it into the old system dynamics terminology from the 50s and 60s. And so it's a little bit frustrating to try and explain to people what is useful about this way of thinking. Now, I do believe that there's some very deep insights in it, but many of them are lost to ambiguity. This phrase that's attributed to either Stu Coughlin or Chris Langton about life evolving to the edge of chaos, there's a very deep insight in Langton's work that leads up to that claim, but my guess is that 90% or 95% of the people who use that term don't have the same understanding of it that Langton originally did, or maybe they don't even understand each other. And so what I'm afraid of is that the community develops a lot of ever are more interesting anecdotes and examples, but we're not really very clear on where this is all supposed to go as an academic paradigm.
Any final thoughts for the interview?
Maybe you will have some social scientists who listen to this. The most wonderful thing I've learned from interacting with natural scientists and computer programmers is that if you ask an intelligent question that reveals you've made an effort, strangers, people that you don't know and may never meet, will really go out of their way to try to help you solve your problem. And so if you feel that you would like to learn how to write a program or study artificial life, you have to dig around on the internet and Google and read email archives and try to figure out as best you can what you want to study. But when you ask a question, you'll be stunned at the famous or helpful people that come out of the woodwork to answer questions for you. And it's been a really wonderful thing, because when I started asking questions about Swarm, Chris Langton, who at the time to me was kind of a mythological hero, when I ask a question and a few minutes later Chris Langton posts the answer, it was really delightful for me. And if people get started, there are other people waiting to help. And then once people get a foothold, they should make a commitment to help the new guys.
Many thanks for the opportunity to interview you.
Well, thank you.